Good day and welcome to our 2018 webinar speaker series hosted by the International Society for Industrial Ecology. My name is Mai Ichihara and I will be your host for today's webinar titled Open Data Visualization Tools. The ISIE webinar series invites leading researchers from various fields to talk about the latest opportunities and developments in industrial ecology. In today's webinar, we will explore open tools for creating Sankey flow diagrams and the use of demographic visualizations of stocks. Here with us are our two speakers for today, Rick Lupton and André Cabrera Serrenho. Dr. Rick Lupton will start by introducing the open source project known as FlowWeaver and its interoperability with other IE tools and data. Then, in the second part of the webinar, Dr. André Cabrera Serrenho will introduce the use of stock demographic pyramids to visualize the interactions between cohorts and service delivery in material stocks. Dr. Rick Lupton is a research associate with the Use Less group at the University of Cambridge, where he is working on data visualization of material stocks and flows under uncertainty. He worked on the Foreseer project, developing interactive Sankey diagrams to explore the water, energy, land nexus, and is the lead developer of the FlowWeaver project. Dr. André Cabrera Serrenho is a research associate in the Department of Engineering at the University of Cambridge, where he has been researching energy and material demand reduction in industrial systems. He developed dynamic material flow analyses to explore the stocks of cars and buildings in the UK, testing the impact of alternative interventions in reducing global greenhouse gas emissions. Before we start, I would like to remind all of our listeners that we welcome any questions you might have, and I will direct them to our speakers at the end of the talk. Throughout the presentation, please type questions directly into the Zoom Q&A window, not to be mistaken for the one labeled chat. And with that, we welcome Dr. Rick Lupton.
Hello, thank you, Mai. Let me just share my screen and then we'll get started. So I'm going to talk about the FlowWeaver project. The aim of the FlowWeaver project is to help you to exchange and analyze flow data and visualize it with Sankey diagrams. For example, here's a simple example of some data on flows of fruit from some farms to some customers on the left. So we have farm 1, farm 2, farm 3, so on, selling to Mary, James, Fred and Susan, different numbers of apples and bananas. And on the right, there's lots of different ways you can visualize that same data as Sankey diagrams. Each of these diagrams tells a different story from the same data. Probably in industrial ecology, we're quite familiar with what I mean by flow data, energy and materials moving through energy and to and from the environment. But actually, in some ways, the scope of the project is wider because many other kinds of data can be thought of as flow data. Money moving through the economy, voters moving between parties, telephone lines moving between providers, and so on. So here's just a few other kinds. This is a Sankey diagram of land use, where nothing is actually moving. It's a breakdown according to different categories. This is an example of flows of voters between parties in the UK 2015 general election. And this is a Sankey diagram of President Trump's tweets and who they were about. So the point is FlowWeaver aims to be a general tool, but it's perhaps particularly suited to industrial ecology type uses. So what I'd like to do in this webinar is to show some examples of what can be done with FlowWeaver, what's already been done. Then I'll spend a bit of time walking through a tutorial, which will show you exactly how to get started using FlowWeaver and point to where to find out more afterwards. Then, as I said, it's an open project, so we welcome contributions from everyone. And there are lots of ways to contribute. It could be programming, but it's also very valuable to use FlowWeaver in your own work, share examples of what you've used it for if you're able to, and give feedback and report bugs and how you found it. So I'll explain how you can get involved at any level for anyone who is interested. And finally, I'll share where I see the project going next and how we're working to create an open data standard for flow data to support interoperability in open science in industrial ecology. I'll start with just a few examples. So here is a Sankey diagram of global emissions of greenhouse gases, broken down by services, devices, and fuel types, and so on. The nice thing about this is that it's all built on standard web technologies. So it's possible to make an interactive visualization that goes on a website and explore different levels of detail. For example, here I've expanded industry to show how much iron and steel is responsible for, and so on. Most of what I've worked on is material and energy flow analysis, but I'd like to make sure that it's easy to use FlowWeaver with all kinds of industrial ecology data. This is a work in progress, but I've been talked to Konstantin Stadler at NTNU about how to integrate FlowWeaver into his package PyMRIO for multi-region input-output analysis. And equally, I'd be very interested to talk to anyone else interested in making similar links to other tools, perhaps including LCA as well, to visualize LCA datasets. This is a process-level Sankey diagram showing exergy flows in a steel-making plant. I think this example shows the value of having a kind of declarative tool that lets you program Sankey diagrams rather than drawing them individually by hand, because here we had data for a lot of different batches, and we were able to create Sankey diagrams of each of them and animate the different batches to see the changes. And obviously that would have been a lot of work if we'd had to draw them each by hand. This is showing exergy flows, but in the data we also had mass flows, and it's, oh sorry, that was mass flows. This is exergy, and it's easy to switch from one to the other. Finally, here's an example where we used it to show uncertainty in different flows. So here the color of the flows shows the level of uncertainty, and that makes it easy to visualize that kind of quantitative information. And again, we can use animation as well to represent uncertainty. So those were just a few quick examples of some of the different things that have been done with FlowWeaver already. So let's dive in and get started using it. I'll open up the web page. Here's the web page on GitHub. If I scroll down, it describes a bit about the project, including that example that I already showed, and then has some instructions for getting started. If you're a programmer, you might want to know that FlowWeaver includes some Python packages and some JavaScript packages that do different parts of the data preparation and visualization, and they can be used independently. But today I'm going to show how they all work together to use in the Jupyter Notebook environment to do some interactive data exploration. So doing this does involve Python, but I found that many people can successfully get the hang of doing this and do the data visualization even without much previous experience of using Python. So here we have instructions for installing it. In practice, you'd want to install it on your own computer for serious work, but you can also try out the tutorials online, which is great for getting a feel of how those work. So I'll click this link, and this is starting up a temporary notebook environment for us. So like I said, any work that we do here won't be saved permanently, but it's a good way of giving it a go. So what's opened here is a Jupyter Notebook. If you're not familiar with it, it lets you interleave some code and writing, text, maths, and the results and plots of the code into one document that lets you describe your work and easily share it with other people. Here the code is already filled in, so we just need to go through and run each part. So I'll just describe how this works going through the tutorial. We'll start by loading some example data. This is the data that we saw before, so it's a table of flows from farms to some customers and describing how many apples and bananas were sold. If we were going to draw this directly as a Sankey diagram, it might look something like this. So here, every line in the table corresponds to one line in the Sankey diagram. But you don't always want a direct correspondence between the flows in your data and the links you see in the Sankey diagram. Often there's too much detail in the data to want to visualize all of it. For example, these farms 4, 5, and 6 are all pretty small. So we might want to group them together into an other category. We can see the flows of apples and bananas are all mixed up. We might want to group those together separately to make it a bit easier to see what's going on. And we might want to group the farms or the customers based on some other attributes. For example, the region they're in, the location, whether the farms are organic or not, and so on. So what we'll do in this tutorial is show you how to use FlowWeaver to do some of these things for this simple example in the simplest possible way. And then we'll point towards some later tutorials that show more things you can do and more efficient ways to doing the same thing. So let's start with trying to do the first example I said, grouping these three farms into one group. The way FlowWeaver works is by setting up a Sankey diagram definition, which describes the recipe for the diagram you want to see, which then you combine with a particular set of data. In this case, we need to start by importing the FlowWeaver package into Python. We then just set the size of the diagrams, and then this is the important bit where we describe some groups. So we've got one group called farms, and that includes the 6 farms that are listed in the table of data as sources. And then we have another group of customers, which includes those 4 customers. We then need to describe roughly how these groups should be placed in the diagram. So this is a list of vertical slices, and this is just saying farms goes first on the left, and then customers goes on the right. And we also need to say which connections should appear in the diagram. So here we're saying we want to include all flows from farms to customers. These 2 steps seem a bit obvious in this simple case, but it's worth being explicit about it when you come on to doing more complicated diagrams. If we put that all together and create the Sankey diagram, we get this. So that is a Sankey diagram. It's the total number of fruit. If I hover over it, perhaps you can see it says there's 46 fruit going from farms to customers, but it's not very useful. What's happened? So here, every farm has been lumped together into one group on the left, and every customer has been lumped into another group on the right. To get the picture that we really want, we need to then describe how to split these apart again to show the categories we're interested in. The way we do that is using a partition. So I won't go through every line, but this is describing a partition which we're calling farms with other, and that has 4 groups in it. So farm 1 is in a group on its own, the same for farm 2 and farm 3, and then there's a group called other, which includes farms 4, 5, and 6. We have another partition which describes how to split up the customers, and here we update the node definitions and redraw the diagram to get something that looks like this. So that's better. We have what we wanted, which is the 3 farms here and then an other category, and the customers shown separately as well. But that's just one way that we might want to break up the data. So perhaps what if we wanted to see how the sales were split between men and women? We can do that just by describing another partition. So here we're describing one called customers by gender, and that has 2 groups. Men includes Fred and James. Sorry for using such stereotypical names, but it illustrates what's going on. Women includes Susan and Mary. And if we update the partition and redraw that, now the same data is shown split into men and women. So like I said, this is showing you the basic way of doing it. It can be a bit wordy trying to write out all of these groups by hand. So there is a better way of doing that where you can include it in the data, but that will be covered in another tutorial. So for now, we'll just show the basic way of doing it. One problem with this diagram is that we've lost track of what kind of materials are going. So whether they're apples or bananas, they're all lumped together into this pinky color. So another thing we might want to do is to split those apart as well. We can do that by describing another partition for the flows, just like we've already split up the processes here and here. So let's do that here. We're describing a new partition which looks at the type column. So if I scroll back up to the top, we have a column type here, which says whether it's an apple or a banana. So we have 2 groups, apples and bananas. We can set some colors. So apples are going to be yellow, bananas are going to be gold. And if we draw that diagram with that new partition, it looks like this. So now we can see that this flow here is green, that's apples. This is a combination of apples and bananas and so on. Now as a last step, it might be nice to label which of these flows are which. One way to do this would be to use a legend to show what color means what, or to put labels on every flow. Another way to do it is to add a new layer in the middle of the diagram, which temporarily groups together the different kinds of fruit as they go from the farms to the customers. We call this temporary grouping point a waypoint. So we need to modify the definition of the diagram to add this waypoint in the middle and then redraw the flows. So that's what is happening here. We're defining a new waypoint. We have to say where it goes. It's been inserted into the middle here, so it comes between the farms and the customers. We're updating the bundle to say that we want to visualize all the flows from farms to customers, and they should go through this waypoint. And if we redraw the diagram, it looks like this. So that's not yet very useful. You can see that the flows are kind of going through that waypoint on their way from the farms to the customers, but the default is to group everything together. We need to set a partition here to describe what we want to do, which is to separate the bananas from the apples. And we can do that here by using the one that we defined before to set the colors. If I draw that, you can see that now apples are all grouped together here, and bananas are all grouped together there. So that's the end of the first tutorial. Hopefully that should have demonstrated the basic idea, which is that we describe a recipe for a Sankey diagram in terms of which processes should be grouped together where, how they should be split up, and how the flows should be split up. It shows that the same data can be visualized in many different ways using different Sankey diagrams, as we've done in this notebook, and also that you can use the same Sankey definition to visualize lots of different data, as I showed you in the example of the videos of exergy flows in different batches. We describe the same structure of the data, but then just apply it to lots of different bits of data over and over again. So that was the first tutorial. Where should we go from there? If we go, sorry, I've lost the website. Let's go back to the website. If we scroll down, there's a link here to find out more. So there's more documentation on this website. This includes further tutorials, so I'm not going to walk through all of the tutorials now, but I'll just give a taste of what they include. I mentioned that it was a bit long-winded to write out details like this every time, such as which customers were men and which were women. So this tutorial on dimension tables describes how you can include that data into your tables of data and use that more easily to change the aggregation. Imports and exports are often something that features on Sankey diagrams. So there's a tutorial here that shows what happens when we move some of these farms or some of the customers outside the system boundary, and we start to get these import flows and export flows, and you can control what happens to them. For example, here, moving the exports up to a band above, if that's what you want to do. I can't see that. Sorry, you can't see my mouse. That's not very helpful. And then we can have more control over how color is used. So we've already seen some examples where color is used for showing different categories, like with the types of fruit. And here's another example with more categories. But we can also use color in Sankey diagrams as a quantitative scale. So here's showing the amount of energy used, and there's various ways that you can customize that to use different color scales for different categories. So there's those tutorials. We're also collecting some more real-world examples. This is a short list at the moment, but we're working on increasing that, and I'll talk later about how you can add further examples to that. There's some more detailed examples here, and this includes the example that's in the journal paper mentioned on the website. And there's also some more detailed API documentation about exactly what all the options mean. As it says here, if there's anything that isn't answered, then please do let us know. You can open an issue on GitHub. So this is, if you're not familiar with it, a very easy way of tracking problems and enhancements to a project. And you can search through what other people have reported or create a new issue if something isn't described. and I would encourage you to do that if you find anything that doesn't work or is difficult to use. And there's also a chat room if you want to ask any other questions. So as I said before, we make an effort to make sure that FlowWeaver is an open project that encourages contributions from everyone, and we make an effort to make sure that it's easy as possible to get involved. And here there's a link to the contributing page, which describes the kind of things that you might be able to contribute and how to get involved. For example, there's a board here that shows things that different kinds of people might be interested in. And I think for this audience, perhaps the key thing here is if you use FlowWeaver to make Sankey diagrams, or you try, then we want to build up that gallery so you can add your own examples to that. And if you tried to use it but couldn't, or had some other suggestions, then please do let us know. That's a really important kind of contribution. But there are other things that can be done. So if you're interested in programming Python, there's various features that can be added there, graphic design. The actual visualization is done in JavaScript. So if you would like to work on improving the layout of the Sankey diagrams, then there's various things that you can do there. In fact, next week, the project is taking part in something called the Mozilla Global Sprint, which is a 2-day hackathon to get a whole bunch of different people to come together in person and online to work on these open projects that support open science and a healthy internet. So if you're interested, I'd really encourage you to get involved, either with FlowWeaver or there's a whole other bunch of great projects that you can look at. So take a look at that. And if you would be interested in working on FlowWeaver, either as part of that sprint or any other time, feel free to let me know. So the last thing I wanted to talk about was where the project is going next. There's some roadmap on here describing how we're working on some short-term things, improving our documentation. But I think a key thing is that we're working on defining an open data format for flow data. So flow data and Sankey diagrams, I think, are quite a core element of the work of industrial ecology. And for open science and the use of open tools to flourish, we need open tools for working with this kind of data, which are freely available, involve the community in their development, and interoperate with other tools and formats. So as well as doing that work on improving the tools that we already had, that's an area that I'm planning to focus on. This is important for interoperability. So we've got lots of tools around for working with Sankey diagrams. There's eSankey, Sankeymatic, a whole bunch more, but they all use different data formats. For example, maybe you want to use STAN for building a material flow analysis, like we saw in the previous webinar with Oliver, but maybe you want to use a different tool to get the right visualization of the results. And so you have to figure out how to convert from the STAN format into whatever format it is for the other tool that you need. And the advantage of having some open data format is that you only need to do all these conversions once if you have some common format in the middle. As well as making it easier to work with different visualization tools, I think this is potentially important for the use of meta-analysis of the results of different studies, which if you publish the results of LCAs and MFAs and so on in a suitable open format would make it much easier to do systematic meta-analysis. As we draft this format, then feedback is greatly appreciated, so please do get in touch if you're interested. Okay, so I'll finish talking about flows there and hand over to André to talk about visualizing stocks, and I'd be happy to take any questions at the end. Thanks.
Thank you, Rick. So, hello, everybody. Rick just talked about some amazing tool to represent flows with lots of flexibility for many different applications. And I just like to talk about some idea on how to visualize stocks. And this idea was actually derived from population demographics. So we need to understand stocks, like stocks of population, to understand that dynamics and to understand what kind of interventions we could do to the population or to the stocks in order to produce some kind of result. So actually, we thought that thinking about the stocks of populations and the way these are represented in these kind of demographic pyramids that we all know could be a good analogy to use for materials and products. So in population demographics, we represent populations in these kind of pyramids representing male and female population, and they give us a picture of the composition of the population as a function of the age of the individuals. In terms of the materials, well, materials, there are no male or female materials, so the representation of these would be just one side of the pyramid, like in the right-hand side of these diagram. And here we could represent the composition, either in terms of number of units, so if we are talking about some kind of product, cars or buildings, or also we can use physical units such as mass or energy or exergy in the horizontal axis. And then in the vertical bars, in the vertical axis, we would represent different age categories of the stock that we would represent. And we could even use different colors to represent, for example, different levels of service that this product that we are assessing is delivering. So the share of these different colors, which is here represented in the left-hand side of the diagram, would give us an immediate idea of the levels of performance in delivering service of this stock of products as a function of their age. So these, of course, could allow us to simultaneously represent stocks, the composition of stocks, and service delivery. This is an example this is an example of an application of these for cars. This is the stocks of cars in the UK for the year 2012. And here are three examples of the application of these. So in the left-hand side, we have the representation of the total fleet in terms of their weight. So the length of each one of these bars represents the total weight of cars on the roads in the year 2012 as a function of the age, which is represented in the vertical axis. But we can also use this representation for individual materials. So in the middle graph, we have a representation of iron and steel, the mass of iron and steel in cars by age of cars. And in the right-hand side, we have a representation of the total mass of aluminium as a function of the age of cars. And immediately, we can see that steel and aluminium have slightly different shapes, and we are using more aluminium in new cars and slightly less iron and steel in new cars. So this representation allows us to understand easily these kind of dynamics and changes that are taking place in the stock. And the different colors in this case represent different types of, different classes of service delivery here in terms of mileage. So the total distance traveled by these cars over a year. These allows us to also understand the relationship between service delivery and the age of stocks. Here is the same representation for the 2002. And by looking at the left-hand side, we see that immediately newer cars, so younger cars, cars with 1, 2 years or less than 1 year, travel more distance than older cars. And we can also use this kind of tool to provide a dynamic visualization of past changes in the stock. And so, for example, between 2002 and 2012, very rapidly understand what happens to the car fleet in the UK. And we realize immediately that the fleet became older. So there were less new cars introduced as we move out from 2002. But when we look into the left-hand side, we see that everything stayed somehow the same. And so this allows us to understand the impact that changes in the product service delivery may have in their rate of replacement. Because by assessing these 10 years of British car fleet, we see that miles traveled decreased substantially at the age that most cars are scrapped, so around between 10 to 13 years old. So we could use this tool to locate what target policies could contribute to extend the lifetime of cars, for example. We can also use this tool to visualize the outputs of prospective stock dynamic models. And, for example, anticipate the availability of end-of-life scrap metals as a function of the age of the cars. So in this graph, this is for 2016, this is cars again. So this is the entire fleet, UK fleet of cars. And in this case, the colors represent different materials. And here in dashed lines, those rectangles are the amount of end-of-life scrap for each material that's removed in this year from the stock. Then we have crosses, red crosses for each age category that read in the top horizontal axis and are a metric of service performance, so passenger kilometer, so the average passenger kilometer per ton of material by age category. So as we move and you run this material and you run this model and visualize what would be the output of this perspective model, we immediately understand and can use this tool to estimate the amount of end-of-life scrap, the impact that the assumptions we used in the model have in terms of service delivery, availability of metals. That could be important, for example, to support investment in scrap handling techniques, or to increase the value of recycled products, or even to assess changes in service performance over time. So we can also use this kind of representation to visualize, to visually assess the impacts of different scenarios that we can build on prospective models. For example, in this case, this is a run of a scenario for the British car fleet again. So we have total mass of the fleet in the horizontal axis, the age of cars in the vertical axis, and different colors represent different types of materials. And in this case, this is a scenario that assumes that some of the mild steel used in cars is going to be replaced by high-strength steel, and we are going to increase occupancy and average intensity of use of cars by 20% by 2050. So, of course, if we increase occupancy, we'll need less cars to satisfy and supply the same service. So we can immediately use this to visualize the impact that this scenario would have in the stock. So we would need less cars. And this also allows us to understand the inertia. So we can easily visualize the impacts of model runs. This could be useful to validate dynamic models, to show the inertia of the stock, so the time it takes to implement changes, and identify the implications of each scenario quite easily by running these dynamic representation. There is no specific open access tool to make this representation, because these technical are just bar graphs that can be built in any spreadsheet software. If anybody wants to look in more detail about the examples I used on these are 2 publications that you could look at. And of course, I'd be more than happy to answer any questions you might have, either here or by email at any time. Thank you.
Thank you, Rick and Andre, for both of your presentations. We will now have a brief Q&A session. Thank you to those who already submitted questions during the presentation. And as a reminder, if you have questions, please type them into the Q&A box and I will moderate the discussion. So we have one question here, and it says, what is the added value of using FlowWeaver as opposed to D3.js for data visualization in Sankey diagrams?
So I guess that's a question for me. I think the added value is in the preparation and the data aggregation that goes on. So the example that I walked through showed how you take the same set of data, but actually when you come to want to visualize it, there's all those steps about what to group together, how to split things apart, which, there's nothing to stop you doing that by hand in a spreadsheet or however you want, and then using D3. It gives you a systematic way of doing that, which you can easily change, and also which you can apply repeatedly to different sets of data for different batches or different time periods or different regions. In fact, the Sankey diagrams that you saw are based on D3. So that's wrapped within the Jupyter notebook in a Jupyter widget. It's based on a D3 library for doing Sankey diagrams. But there's no reason why you couldn't use the data aggregation preparation side of FlowWeaver and then use a different D3 library to actually visualize it if you wanted to.
Great. And the next question, in the representation of stocks, could you modify the thickness of the bars to show a variable?
Hello. You could modify the thickness of the bars, definitely, to show an even more to add more variables to the representation. I just wonder what would be the compromise of the easiness to visualize all the variables by doing that, because in that case we would have different thicknesses around the graph. But yes.
Great. And another question here. Do either of you have any real-life examples of how these tools are being used in current research on specific industries or materials?
Would you like to?
So I guess some of the examples that I showed explain that on work that's been going on here. So there was looking at mass and XG flows in a steel making plant at the batch and process level to find opportunities for resource efficiency. And there's a paper published on that, which maybe I should have included a link to, but those are available. Other work has involved looking at the useful energy balance for the UK, looking at European sales of flat steel according to different characteristics, such as thickness, grade, coating, and so on, which is actually that's where this project really got started, was the need to take that detailed data where it's not just working in terms of tons of steel, but we're disaggregating that in terms of tons of 3mm thick uncoated steel, as opposed to 2mm thick galvanized steel and so on. That's when we really needed this capability for dealing with different attributes and grouping. Yeah, and I think those are the ones that we have most detail of, but I know that other people are using it in other non-industrial ecology settings for doing some Sankey visualization as well.
Great. And another question, is it possible to include data uncertainty other than Gaussian normal distribution?
Yeah, so that's an interesting question. The example that I showed, maybe should I put that back? So this example was my work on Bayesian material flow analysis. So that allows you to use arbitrary distributions, and we calculated the uncertainty by sampling using Markov chain Monte Carlo. So we had hundreds of samples, and we used those to estimate the uncertainty intervals, which are shown using color here. So I don't know if you can see at the bottom, there's a color scale where dark blue is 0 uncertainty interval, going up to the pale yellow is 700 megatons uncertainty. So roughly these bright yellow flows at the top, the uncertainty is the same order of magnitude as the flow, and so on. And there's more details about that in the paper. But yeah, that is based entirely on that non-Gaussian one. The interesting thing as well about this uncertainty in Sankey diagrams is that the color shows the uncertainty of each flow independently. It doesn't show how they're related to each other. But actually, here, for example, we have several parallel flows, and the uncertainty is about what the distribution is between those. So if we're uncertain about the size of this process, if it's smaller than is shown here, that necessarily means that these other two must be bigger. There's a lot of correlation between them. And that's hard to show in the Sankey diagram. But in this video, some people find this unsettling to watch, but it does show that correlation. So you can see that in the frames when this one is small, these ones are big, and vice versa. So that's another way of showing complicated uncertainty. But from the point of view of FlowWeaver, then the color is just based on some attribute of the flow. You can use color to show the magnitude, to show the temperature, energy intensity, anything you want really. So it's definitely can be used to show non-Gaussian uncertainty, yes.
Great. And next, could this be used for visualization of results of statistical analysis? For example, analysis of correlations, where a large number of correlations is analyzed and should be visualized for better understanding.
That sounds like an interesting idea. I suppose I'm not sure if I understand what the person asking the question had in mind, but maybe you could imagine visualizing the correlations as a Sankey diagram themselves, where you have the same set of variables down both sides, and the links between them show the size of the correlations. That could perhaps work. And definitely you could visualize that. So you would want to describe the correlations as a table, where one column was the one side of the correlation, another column gave the second variable, and then a third column gave the strength of the correlation. And then that would be a straightforward Sankey diagram that would show all the pairs of connections between the two. I'm not sure if that was what they had in mind, but I expect it could be done. If they would like to talk about that more specifically, I'd be happy to hear from them.
Thank you. And Rick, you mentioned that FlowWeaver can be used in LCA. Are there examples of this out there today?
No, I don't think there are. So I would like there to be examples of this today. So whether that's visualizing whole analyses, or whether it's linking into databases to show the visualizations of particular unit processes, might be interesting. Yeah, I did want to put together an example for this webinar, but I didn't have a chance to do that based on LCA specifically. But again, if anyone would like to do that, then I'm happy to hear from people.
Thank you. And have you considered integrating the stock diagrams and the flow diagrams shown separately today in order to visualize more complex system dynamics?
That sounds a good idea.
I think maybe we've considered it, but yeah, we don't have anything to show for that. Do you want to say anything about that?
No, I could imagine at some point could be useful to link Sankey diagrams to stock demographic pyramids. And in that kind of representation, we could play with the thickness of the bars, linking the bars directly with flows. And we could make it dynamic. Although I'm not sure about how easy that representation would be to intuitively understand by looking at that complex diagram, what's going on. And also that somehow there is a problem, because then the thickness of each bar in the stock pyramids would not necessarily coincide with 1 year, for example, if that's the unit we are using for the age category. But in theory, yes, that might be helpful for some applications, definitely.
Great, thank you. And for both the stock diagrams and FlowWeaver, what are your hopes for the future in terms of further advancing the technology and visualizations? What do you hope these tools will be able to do in the foreseeable future?
Mm-hmm. So I can start for FlowWeaver. So I talked a bit about wanting to develop an open data format. So that could be seen as providing, that would be the output of FlowWeaver. You'd collect your data, you'd process it, and you'd end up with a description of a Sankey diagram, which then you could integrate into other tools. Maybe there are some better Sankey diagram editors for tweaking it for publication or whatever. So you can continue to use that linked into other tools, and that's something that we should definitely be working on. The actual visualization I've shown works well enough for the simple diagrams I've used in the example, but you start to run into limitations of the automatic layout once you start to look at more complicated diagrams. So I think that's something that could definitely be improved, drawing on some work in computer visualization of other kinds of graph structures. And I think the other area that I could see being improved, maybe in the longer term, would be in smart tools that make it easier to describe these Sankey diagram definitions. So it works well because it's quite explicit about what you want to see, which means you can program the diagram that you want to end up with, and like I said, reuse it for lots of different kinds of data. But in some ways, there's a little bit of boilerplate. You know, you have to write out some quite basic stuff to get started in simple diagrams, and so making that more automatic would be an interesting area to work on, I think. But I think in the immediate term, making it tie into other tools, work with, for example, an MFA done in Stan, which could then be processed using FlowWeaver, I think would be a great development.
Just to add in terms of the stock dynamics representation, I think, well, for material flow analysis, data availability is usually very often one of the main obstacles. That problem is even greater for stock analysis, because we are adding another dimension, which is time, to the analysis. But if in the future we are able to compile coherent data sets that allows us to add resolution to the composition of stocks, and to use that resolution to more detailed applications of existing products, then we probably will be able to use this kind of representations to address much more specific problems in specific stocks, and create hopefully more reliable prospective models that allows us to understand what are the future implications of some actions that we can, and some interventions that we can do to stocks of products and materials now.
Great, thank you both. We've answered all the questions. So with that, Rick and Andre, did you have any last comments or thoughts you'd like to share?
I've no further comments, and anyone who has any other question later, I'd be more than happy to reply by email at any time.
Yeah, thank you to everyone who asked questions. And like Andre says, I'm happy to continue the discussion afterwards. But
Great. So with that, we conclude today's talk on open data visualization tools. Rick and Andre, thank you so much for joining us today. And to view a recording of this webinar, please visit the member portal on the ISIE website. The video should be posted by the end of the day. Thank you, everyone.
Bye.